Hello everyone and greetings to the Machine Learning Security Evasion Competition 2020. My name is Zoltán Balázs and I am the head of Vulnerability Research Lab at Gujo AI. I had a lot of different offensive researches in the past, like the Zombie Browser Toolkit, the Hardware Firewall Bypass Tool, the Malware Analysis Sandbox Tester Tool. I also played with some crappy IoT devices, and my remote code execution exploit actually appeared in the Persirai botnet running on 600,000 IP cameras. And I also invited the idea of encrypted exploit delivery, the Diffie-Hellman key exchange. I'm the co-organizer of the Hackerschule meetup, and I'm the program committee member of the Hacktivity conference. This is a joint project together with Hiram Anderson, and he is the architect at the Azure Trustworthy Machine Learning at Microsoft. And machine learning security is his first class, and he's also the co-founder and co-chair at COMMSEC. He has a background in signal processing and machine learning, and also in information security. And he is also the creator of the GIM malware research, which is using reinforcement-based learning to evade antivirus detection. And he is also the co-creator of the 2017 and 2018 Ember datasets. When it comes to machine learning, there is the common problem where a machine learning classifier has to classify an image. For example, correctly working machine learning algorithm should classify both the image on the left and the image on the right as a bus. But there has been some research where some special noise has been added to the image, and now the machine learning classifier mistakenly will classify the image on the right as an ostrich. There have been also research in the past how real-life machine learning-based malware detection can be bypassed. For example, one research appended the strings from a known game to the end of a known malware, and they were able to bypass the machine learning malware detection easily. In the past, I also played a little bit with machine learning detection bypass, and for example in 2016 it was even possible to bypass machine learning detection just by using a simple packer SUPX on the malware itself. As of the first research, you can find the relevant material on the URL below. Hiram and me had the idea that maybe we should create a competition around bypassing machine learning-based malware detection. And our purpose was to advance the field of offensive and defensive machine learning-based malware detection. The way the competition worked is that you had to download 50 working malware samples, download 3 different machine learning models with its weights, so this was basically a white box attack, modify the malware samples to evade detection by all models, and if you were the winner, you could win a nice NVIDIA Titan RTX GPU. And the whole competition was announced at the AI Village at DEF CON 17. At the end, 70 people registered for the competition, and 11 contestants was able to bypass at least one machine learning model. And the winner was William Fleshman. You can find his write-up on the following URL. And if you are interested, you can also find other write-ups from other competitive teams. For example, here is one from Jakub Debski. And here's one from Fabrizio. There were different approaches used in this competition. For example, some people tried to pack the samples with a packer, which is a nice idea, but unfortunately, because some real-life malware is already packed, if you pack it again, there are chances that it will not work. But clearly, this is a competition-specific issue. Here you can find a nice, like landscape of how packers can be classified in the wild. Another approach was adding new sections to the executable, and instead of using random sections, it's even a better idea to extract some resources from known Microsoft files, for example, and add these as repeating sections to the executable. This approach works most of the time, but sometimes it can break the malware, unfortunately, because malware can have some self-checks and adding new sections can break it. Also, fun fact, just by adding a new section to malware, you might be able to even bypass some antiviruses. I guess this is because of performance reasons, where the AV engine first checks how many sections are in the sample itself. And here you can find nice Lief-based code on how it's possible to add sections to an executable. It's pretty straightforward. You can also just easily append some extra data to the executable. This is a similar technique as I already discussed with you when the strings from the Rocket League exec game has been appended to the Mimikatz. And turned out that this was the winner strategy at the end. Funny thing is that it's very dumb and plain solution, but still it works. The winner strategy was using brute force, which was easy to implement when you are attacking the machine learning models as a white box attack. Unfortunately, this attack will not bypass antivirus signature checks unless the AV checks for the file size, again, for performance reasons. On the top image, you can see the visualization of a malware sample. And here you can see how it looks like when some repeating text data has been added to it. You can clearly see that the new executable includes the original executable at the beginning. Some key takeaways from this competition was that the malconf and non-malconf machine learning models used in this competition were too academic and they were not very effective in practice. The Lief project is awesome, and dealing with malware can be pretty tricky. For example, some samples do not reproduce the same IOCs over time. It can be because CNC is down or something similar. And also packed and protected samples are unfortunately hard to deal with. But hey, that's the challenge. Also, I was checking some of the solutions with the SSDeep hash, and turns out that if someone is adding repeating patterns to the file, either via sections or just repeating overlays, it will generate a repeating pattern in the SSDeep hash as well, which is quite funny because just by looking at the SSDeep hash, you can see that something fishy is going on. No legit executable SSDeep hash should look like this. In 2020, we upgraded the competition and we created the Defender Challenge track as well, where you had to create your own machine learning model and submit it to the competition via Docker format. And we kept the attacker challenge, but now instead of white box, it was a black box attack, because the only available model for you was the Ember model, but the machine learning models submitted in the Defender Challenge were not available as a white box to the competitors in the Attacker Challenge. It was only a black box. The sponsors and partners of this year's competition was Microsoft, Kujo AI, VMware, and MRG Effitas, but the main organizer people remained the same. And this year you could win Azure credits for your machine learning research plans. On the defensive track, 2 submissions passed the minimum requirements, and it was the Need for Speed and the random string domum-pick-b. In the attacker track, you could have expected the following malware families, which you had to modify in order to bypass the machine learning models. So this year, if you were in the attacker challenge, then you had to register at the commsec.io, review the terms of service, download the 50 provided malware samples. Somehow you had to modify the malware samples, verify that the malware still produces the same IOCs and behaves the same. You should use a Windows 10 virtual machine for this purpose. You can also use our API to upload the samples, or just use the regular web interface. And you could get up to 3 points for each samples based on how many machine learning models you were able to bypass. And the highest score wins. And in order to receive the Azure credits, your solution had to be published, for example, in a blog or something similar. Whenever you upload the modified malware samples, please be mindful to keep the file names as they were. Otherwise, we have no idea which file has been modified to which file. And we really need this. Some tips and tricks we provided this year for the competition. For example, you can add or remove digital signatures on the executable file, change section names, properties, modify the imports or exports, create some TLS callback, change the PE header, fix or change the checksums, add, modify, or remove version information, create new entry points, change some code, for example, or data which does not change the behavior of the file itself. It was not allowed to use any droppers, and multiple registration is against the rules. And you can still join our Slack channel, so you will be able to see any updates to the competition. The whole web frontend was based on Python Flask admin, and we were using Cloudflare, Nginx, and GUnicorn for scalability and performance. The backend scripts were developed in Python, and we were using the VMRE sandbox to check whether the sample produces the same IOCs as before. We also created an API, so you don't have to use the web user interface. For example, if you want to submit a sample to check with the ML models, then you could use this API query. Or if you want to submit your sample to a specific ML model, you could do that as well. You could get the ML model results with the following GET request. You could also upload your files for checking with both the machine learning models and the sandbox with the following form. You can get your zip status, or you can query all sample status with the followings. Or if you are interested, you can get get data from a specific sample. So if you visit the commsec.io website, first you can review the terms and services, and after we also recommend that you check all the readmes for both the defender and for the attacker track. For example, here you will see some sample solution Hiram prepared for you. Now, if you go to the register login, you can use either Microsoft GitHub or Google to login. And for the attacker track, you can download the malware samples there. And if you look at the malware samples, you can see that they are these sequentially named files. And once you modify and test your malware samples, you should create a zip file with the similar structure. And here you can upload your modified zip file. Here, as you can see, there are the same file names in this zip file. You can also add a custom label to this upload. And once it's uploaded, you only have to sit back and wait for the results. In this test upload, I did not start the processing, but you will see that it is processed in the it is submitted to the machine learning backends. You get the results for the different machine learning models. Then it's also uploaded to the VMRay sandbox, and it's analyzed whether it has the same IOCs generated or not. On the user management part, I highly recommend that you create your cool new nickname. So on the leaderboard, you can see your nickname and not some randomly generated strings. And keep in mind the total API queries number, because if you have the same score as someone else, the total number of API queries will decide who wins the competition. The less, the better. And let's continue. Now, the winner of the 2020 Attacker competition was Fabrizio and Marcus, and you can find their solution on the following URL. And the winner of the Defender track was Erwin, Lucas, Maiko, Daniel, and Konrad from Germany. Congratulations to them as well. Their white paper can be found on this link. Fabrizio and Marcus was also kind to create a white paper for their Defender solution, which was the second, which you can find here. And on the Attacker track, the second place goes to Wander Wuzzi, also known as Johann Rehberger from Germany. So as for the Attacker winner strategy, they were using base64 based obfuscation and a lot of dead imports to the import table. And the Defender created the so-called PE bears Docker image, which use different machine learning models, semantic gap detectors, and the stateful defense. And their solution was a combination of these. In total, 60 people registered for the competition. And as mentioned, 2 people submitted a valid Docker image. 5 people were able to bypass at least a single machine learning model while preserving the malware functionality, and the ML engines were checked. ML engines checked 5,654 samples. Also, if you check out my blog post, then you can see some real-life results of some of these techniques, how you can use these techniques to bypass real-life either antiviruses or machine learning models. That's all I wanted to share with you, and now the floor is for Hiram, who will show you his tool and how you can use it to win this competition, maybe in the Machine Learning Security Evasion Competition 2021. I hope you guys enjoy this, and the floor is yours, Hiram.
I'm going to be presenting the Machine Learning Evasion code walkthrough. This tool was included in the sample solution to the Attacker Challenge in the Machine Learning Security Evasion competition. You can download and play with this code by visiting mlsec.io and navigating to the Attacker Challenge GitHub repo. Our example solution was designed with the following things in mind. Number one, the models to be attacked were submitted by contestants in the Defender Challenge that concluded previously. 2 models from the previous round qualified to be included in the Attacker Challenge. In addition, we have hosted our own model to be attacked that is based on the Ember dataset. The models to be attacked report hard labels for submissions provided to them. That is, they do not provide a score between 0 and 1, but just a 0 for benign and 1 for malicious. Finally, we considered the leaderboard criteria while designing our solution. The first criterion considers the number of model evasions. With 3 models and 50 malware samples, the maximum score is 150 points. A tiebreaker would be decided by the efficiency in which the models were evaded. So we count the number of model queries. Thus, contestants are incentivized not only to be evasive, but also to do it efficiently. Contestants were able to choose any strategy that they like. To demonstrate one strategy, we released this example code on our competition's GitHub site. The code uses discrete optimization over functionality preserving file modifications using a package called HyperOpt, which ironically is often used for tuning machine learning models. You can learn more about the details from the code and documentation on the website. However, the broader strategy may be of general interest. It consists of employing an algorithm in part A to get the bulk of the malware to be evasive while remaining functional, followed by any additional manual steps in part B to fix any few remaining samples. We use the example code in our strategy in part A, in which we break our algorithmic attack into 2 phases: an offline attack against a known defender model for which we have code and weights, and an online attack. The hope is that many of the samples that were discovered in the offline attack will cross-evade the hosted online models without having used any additional queries against the API. You may visit mlsec.io to download this code. However, please be warned that when you run this demo code, you will write functional malware to disk. So please do so only using a Linux VM. To begin, we initialize the attack by analyzing a collection of benign files. The init subcommand extracts elements of the benign files that will be injected later into the malware. To launch our offline attack, we first run a local copy of the Ember model in the top window. Then in the bottom window, we'll use the run subcommand of our attack script, passing in malware samples that were downloaded by contestants. The tool will write successful evasion attempts to pass1/success and failed attempts to pass1/failure. Also included in each directory are history files that would allow us to resume our optimization of failed attempts. In the second pass, we begin with only the pass1 failures and iterate on the optimization, again storing successes and failures to a folder of our choice. Having now collected candidates that evade the Ember model, we use those candidates as seeds for an online attack, which now counts against our API query usage. The online attack is enabled with a simple -- online flag. After several iterations, we can now gather the successfully evasive variants and create a zip file to be uploaded to the website. Since there is a chance that the file modifications have broken some of the files, contestants have been encouraged to run the samples in a Windows 10 sandbox to validate functionality before uploading to the competition website. As a final note, since the hosted models may learn from the queries issued by contestants, there is a possibility that an evasive variant discovered by a contestant at the beginning of the competition may no longer be evasive to a model by the end of the competition because the model has changed its state.
So thank you everyone, and see you at the Discord channel for questions and answers. Goodbye.